Hi, my name is Shunyao. I'm an undergraduate student majoring in electrical engineering at RPI. During this semester, I'm working with Grid X team on machine learning application for a fast detection of force oscillation. This is the outline of my work. I'll first talk about my objective and the method I use, including the Waveform SDK and the sockets. After that, I'll go through the hardware's specification, my implementation, and the result I got based on the implementations. Finally, I'll talk a little bit about my future work. For the objectives, the first thing I need to finish is to developing data acquisition method use ADS 7823 and PCF 8591 on Jetson TX2. So ADS 7823 is a 12-bit ADC and PCF 8591 is a 8-bit ADC. Secondly, I need to use Waveform SDK to generate a customized signal from analog discovery 2. The signal should be something like several different types of signal in a row and also cannot kind of blending different proportion of sinusoidal wave and noisy wave. Then I must develop a method to automate experiments since performing large number of experiments manually is time consuming. Finally, I need to do the experiments. So let's talk about the method I use. So Waveform SDK is available and supported in Python and C++. It provides access to a public API that allows users to interact with Analog Discovery 2 and create customized PC application. This table shows 9 main groups of API functions, each named with different prefixes. And then let's talk about the socket. The socket and the socket API are used to send messages across the network. Sockets can be configured to act as a server who listening for incoming messages or as a client who connected to other applications. I use sockets to automate the experiment since the communication between my laptop and the Jetson TX2 is needed during the process. The client, which is my laptop, need to tell Jetson TX2 the server when it should start to inference and when it should stop the inference. The diagram below shows the sequence of socket API calls and data flow for TCP. Starting in the top left-hand column, noting the API calls the server makes to set up a listening socket. A listening socket does just what it sounds like. It listens for connections from a client. When a client connects, the server calls a accept command to accept. In the middle is a round trip session, where data is exchanged between the client and the server using send and receive command. At the bottom, both the client and server close their respective sockets. Then let's talk about the hardware specification. So as I mentioned in the objectives, I'm going to use two types of analog to digital converter, which is ADS 7823 and PCF 8591. The EDS 7823 has two modes, the standard mode and the high-speed mode. I'll also use the Jetson TX2 to run the CNN model and do the inference job, and the analog discovery 2 will be used for generating signals. For the implementation part, I'll first talk about the data acquisition method. For performing data acquisition, use PCF 8591. The first thing I did is install SMBus library in terminal of Jetson TX2 to interface with our PCF 8591. The command is also copied here in this slide. Secondly, in order to check our ADC's I2C addresses, we need to type in the following command in the Jetson TX2 terminal. The figure below is an example of how we find the addresses. So this is the code organization. In part 1, I import all the libraries, and in part 2, I load our CNN model. And then in part 3, I initialize the I2C bus and use the address we find in the last slide to set the value of our local variable. And the rest of the code is used to connect data and perform inference. So the figures in this slide are basically the circuit schematic and picture of my setup. The code for data acquisition use ADS7823 is slightly different from PCF8591 since ADS is a 12-bit ADC and PCF is just a 8-bit ADC. The register's address is changed and now we need to read 2 bytes from the register and convert them to binary number. The second part of my implementation is use Waveform SDK to interact with Analog Discovery 2. These are the functions I use to open and close devices. And these are the functions I use to set the parameters of the signals. So the first thing we need to do with Waveform SDK is to generate several different types of signals in a row, since we are going to test the validity of our CNN model and experiment with different data acquisition methods. And we can generate the signal as shown in this figure, which consists of both noisy signal and oscillation waves. This is my code organization. For the first part, the code asks users to import 3 values A, B, and C. All these values correspond to the time length of different phases. For example, if I input n 5 to the variable A, it means that the first phase, which corresponds to the sinusoidal wave, will last for 5 seconds. And the second part of my code just declare 2 C-type variables use the C-type library. So the third part of my code is to print the version of the DWF. And the first part is to check if the device is connected, and the last part is to generate the signal. So the second task we need to perform with Waveform SDK is to blending different proportion of sinusoidal wave and noisy wave. Since we're going to test the noise sensitivity of our CNN model, we use different data acquisition method. Figure on the left shows a signal customized by our code with small noise, and figure on the right shows a signal with large noise. So this is the code organization I use to customizing the signals. For the first part, we just declare 3 C-type variables, use our C-type library. The RGB samples here is a C-type array contains 4096 double elements, and it means that there are 4096 samples that define one complete cycle of the waveform we design. And in the second part, we just fill in this RGB samples with the proportion of sinusoidal wave and noisy wave we want. And in the third part, we generate our signal with frequency equals to 100, which means that we need to sample all the 4096 samples 100 times per second. So the third part of my implementation is to automate the experiment use sockets. This step is very important because it it will be time consuming for me to do all the experiments manually. So let's first talk about my code on the server side. So I first start by creating a socket on the server and then use the bind command to associate the socket with the server address, and the port number is 10,000 in my case. And then calling the listen command puts the socket into server mode, and the sap command wait for an incoming connection. And after the connection is built, the data can be read from the client with receive command and transmitted back to the client with send all command. And finally, when communication with the client is finished, the connection need to be cleaned up using the close command. On the client side, the code is basically the same. Um, so we start by creating a socket and set the server addresses and the port number. And after the connection is established, data can be sent through the socket with send all command and received with receive command, just as in the server. And after the entire message is sent and the copy received, the socket should be closed to free up the port. And then we comes to the result part. This is an example of inference result when perform data acquisition use ADS7823, and total inferences is 71, and the number of errors is 0, so the accuracy is 1.0. For the data acquisition use PCF8591, there's also an example of inference result. The total inferences is 131, and the number of error is 3, so the accuracy is approximately 0.9771. The figure above shows an example of generate different types of signals in a row using Waveform SDK interact with analog discovery 2. The signal generator first sends a sinusoidal wave. After a while, it shifts to send a noisy signal with a smaller amplitude, and finally back to the sinusoidal wave. All the parameters, including time, frequency, amplitude, and offset, can be adjusted in the Python script. So this video shows how the signal generated in the last slides looks like. The figure above shows an example of blending different proportion of sinusoidal wave. Use Waveform SDK interact with analog discovery 2. The figure on the left side is a sinusoidal wave with small noise added on it. The figure on the right side is a sinusoidal wave with large noise added on it. The ratio of sinusoidal waves amplitude to noisy waves and amplitude can be adjusted in the Python script. So for the experiments, the first experiment I'm gonna present is the frequency variation experiments. So first for the ADS7823, I performed in order to test the limit of the um, testing range. I performed 300 experiments on ADS7823 from 1 to 300 Hz, while keep the amplitude constant. Use the automation method described in the slides 19 to 21. Each experiment was performed based on an identical and 30-second input signal. The blue line shows the accuracy corresponding to each frequency value, and the red line shows the total number of inferences performed during each experiment. So the data collected in this experiment can also be drawn as a semi-log diagram. In this diagram, we can clearly see where the inference accuracy drops dramatically. Based on the graph, the detection range of ADS 7823 in standard mode is 0 to 280 Hz. So since the detection range of ADS7823 in standard mode is 0 to 280 Hz, as explained in the last slide, I performed 100 experiments from 0 to 280 Hz. The data collected from this experiment is drawn on the left. The data of frequency variation experiment for PCF 8591 is also drawn here. And then the semi-log diagram. In order to compare the performance of the ADS and PCF, we drop a histogram. The blue one is for the ADS, the orange one is for PCF, and the mean variance standard deviation is also calculated on the right side. The mean of the ADS is much higher than PCF, and the variance and standard deviation of ADS is much lower than the PCF. So that means the ADS is much reliable than the PCF, and it also has a wider detection range. And secondly, we also perform the noise variation experiment for ADS and PCF. So first for ADS 7823, the signal generation method explained in slide 23 and 24 is implemented in this experiment. There are 100 experiment again, and the ratio of noise wave amplitude and sinusoidal wave amplitude is increasing from x to 1 as shown in the x-axis this graph. And the data collected in this experiment can also be drawn as a semi-log diagram. And this is a noise variation experiment for data acquisition method use PCF 8591. And this is the semi-log diagram for that experiment. So again, we compare the performance of ADS and PCF, and we drop the histogram, we calculate the mean variance and standard deviation, and the mean for ADS is still higher than PCF, and the variance standard deviation for ADS is still lower than the PCF. So that means the noise will affect the PCF 8591 more than the ADS 7823. So ADS is still more reliable than the PCF. So finally, I will talk about my future work and next steps. So my future works contains 3 tasks. The first task is to use 3 types of data to train our convolutional neural network model. So the first model should be trained by the simulated data set generated by Python, and the second should be trained by the data set generated from analog discovery board 2 captured by Jetson TXU, and third model should be trained using using the dataset contain X% from the dataset used to train model A and Y% from the dataset used to train model B. And the value of X and Y need to be determined in the later experiments in order to achieve the accuracy and speed rate of detection algorithm. So the task 2 is to add the digital output after data is received by Jetson TXU, and the task 3 is to perform training testing and real-time experiment use simulation model of waveform.